Yeah. All right, but anyway, so example 3 kind of sort of looks like arctan. So, or at least it has the x squared plus 1 in it. That's consistent with the arctan. Maybe in the current form it doesn't kind of sort of look like arctan, but if you rewrite it as dx over the square root of x squared plus 1 cubed, you have that radical x squared plus 1 component, that the radical with the sum of squares in it, that you become accustomed to seeing when an arctan is involved. All right, so when that happens, we know that we're looking at a u and an a. So the u is equal to x, the a is equal to 1. And so we label up our triangle. The labels that we're looking for are ones that would give us, when we put the x and the 1 in the triangle, the u and the a values, a missing side of square root of x squared plus 1. All right. So if I were to place, and you could do it with trial and error, that's a worst case scenario, but if I put the x here and the 1 here, the hypotenuse would be square root of 1 plus x squared, or square root of x squared plus 1, either way. All right, because addition is commutative. So you have a choice in how you want to write it. I want to write it this way because that's consistent with how my integral is presented. All right, so good to go there. Now what I want to do is create ratios. The ratio of the variable to the constant, and then the ratio of the radical to the constant. Fortunately, the constant's equal to 1. That's great news. All right, so that's telling me that I have a ratio of x over 1. That's the tangent ratio because we're looking at the opposite side. I used the wrong colors. Hold on. Beep, 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 beep. I want to go blue for those keeping score at home. So the tangent ratio is equal to x over 1. All right. And the ratio of the radical to the hypotenuse, that's the the radical to the constant is the hypotenuse over the adjacent, which is the secant ratio. So secant of theta is equal to the square root of x squared plus 1. So this one's a little bit nicer than the previous ones, over 1, because the over 1 part becomes irrelevant. We don't need it. All right, so you could just think of it as x equals the tangent of theta. So I'll just rewrite x equals tan theta. You can think of it as the square root of x squared plus 1 is equal to the secant of theta. All right, so I just need a dx, which I would get by taking the derivative of the x equation. So dx would be equal to secant squared theta d theta. So now I have all the ingredients, ready to rock and roll here. All right, so I'm looking at an integral. Instead of the dx, I'm going to put a secant squared theta d theta. On the bottom, instead of having that radical x squared plus 1 cubed, I'm going to have a secant cubed. Simplify that, you get 1 over secant d theta. But 1 over secant is the same as saying what? Cosine. The antiderivative of cosine is sine. So we have sine theta plus c. So we took something that in its original form wasn't really antidifferentiable and made it nice and convenient. Right? The one issue that we run into here is that we can look all over the work that you produced already, and you're not going to see a sine theta anywhere, because we didn't need sine theta to do our substitution. But we have a triangle, and that triangle, I didn't write it in there because, force of habit, but there's a little tiny theta in there. When you have that little tiny theta, that means that the side opposite that theta is the opposite side. Then you have your hypotenuse, which is the side opposite the 90-degree angle. If you want the sine of theta, you just need to identify the opposite side and the hypotenuse. So this becomes x over the square root of x squared plus 1 plus c. All right, it's a nice solution. You know, emerging from really nothingness. You know, like you stare at that when you look for a u substitution, not going to work. Right? You try to shoehorn it into an inverse trig rule with mixed degrees of success, I suppose. Maybe you try a little guess and check. That could work sometimes, by the way. I mean, I actively discourage that unless it's an absolute last resort. Right?
So in terms of like a question like this, on a test, like where, I don't know, I guess where does,
Is the question like, so in terms of a question like this, what?
it's,
Indicating like, what the hell is this? Or
no, it's more of a, to get full credit, you get, I don't know.
to get full credit, we start with the final answer.
Yeah.
I mean, you get that,
Yeah.
then you're in the right neighborhood. But the thing is, you know, you saw the breakdown, right? If it's a question that asks you to do it by trig substitution, then you're on the hook for that approach, right? Now, I will tell you, just a spoiler, I did not, in many circumstances, ask you to do it in a particular way. So I gave you the breakdown on the test. Number one, I said was a u substitution question. Number two, I said whatever it was, right? So on the test, it's going to say integrate. It's not going to say using u substitution. It's not going to say anything. Because what I wanted to do is leave you the avenue to get creative. You know, like if you get jammed up, you try to do it with trig substitution, for example, that particular question, and you run into a roadblock and you're like, I just can't do it. I don't want you to leave a question completely blank because you just drew a blank on the concept. So you'd still have a fighting chance of getting a complete solution. So you can do it any way you want. That breakdown that I sent you is the way to do it. Like, it's the best way to do it. Like, for an integration by parts question, I struggle to come up with other alternatives. Like, I don't know situations where, if you're given a question that needs to be done with integration by parts, where you could use another technique, unless you're really, really savvy and you can do some serious guessing and checking, I don't see how you're going to come up with it. All right? But there are situations when it comes to trig substitution where you can get away with other techniques. All right? And we'll get to that in a few minutes. All right? So you do have avenues, all right, if you're in a jam. All right? I don't want to call it like suggested approaches when I give you that breakdown, because in reality, when I say number one is u substitution, that means the right way to do it is u substitution. You might find another way to do it that will also give you the right answer, but it's not going to be as easy to do as u substitution would be. All right, so, but you can still get the job done. All right. It's like nail gun versus hammer, if you understand that reference. I only know that because I have built a house before, and the air compressor broke. But there were plenty of hammers, and it sucked. We didn't have to do the whole house, but for one day, there was no nail gun available. And it was like, all right, well, nail guns didn't always exist, so here we are. Everybody grab a hammer, grab some nails, and get to work. It was brutal. I never recovered, actually. Number 4, again, trick question on a test. It's a definite integral. Pop it right in your calculator and don't even look back. But you also want to be prepared for the event that, hey, you know, let's say these two bad boys aren't there. You know, you're starting to get a sense of my personality at this point. you could actually see this problem without those bounds being on the test, right? I'm not saying I did that though.
So should we just do it without?
So we're gonna do it as if their bounds weren't there. Yeah, just so we get a good feel on how to approach this kind of problem.
X down.
Yeah. All right, so we have an x squared minus 3. So that's the key ingredient. That x squared minus 3 is telling me that the u is equal to x. The a is equal to the square root of 3. All right, because it's the square root of each of the terms that give you the u and the a. All right. Regardless of the fancy rules on the opening page for this section, all I need to do is place these values, x and root 3, in my triangle in such a way that the missing side ends up being the square root of x squared minus 3. All right, so that's what I'm going to do. So I'm going to pop it in there, put my theta in there this time. All right, so if it's going to work out so that x squared comes first, that means that the x has to be the hypotenuse. All right, now I can put the radical 3 in for either of the two legs. It just ends up being more convenient if I put it for the adjacent side. All right, the way I know that that's the more convenient way to put it is because I will have created a ratio of hypotenuse to adjacent, which is secant. If I put it over here, I will have hypotenuse to opposite, which is cosecant. Generally, you want to stay away from the cos. It's not wrong if you include a co, but it's not ideal. All right, so the missing side is going to be the square root of x squared minus 3. And so I just need some ratios. I need ratio of the variable to the constant. So that's the secant of theta is equal to x over root 3. And you do enough of these problems, you realize that eventually you're going to have to solve for x anyway, so you might as well just do it. X equals root 3 secant theta. And then the other ratio is going to be the radical to the constant. And so that's opposite over adjacent, so tan theta is root x squared minus 3 over root 3. Ultimately, I want to get rid of, in the integral, I want to get rid of that radical only. So, I mean, I want to get rid of the x too, but I want to get rid of the radical first. So I'm going to solve this for the root, the square root, or let me make that a little bigger. X squared minus 3 is equal to root 3 tangent of theta. All right, I'm going to rewrite my integral, but I'm going to leave off the bounds, all right, because I'm going to create an integral that's in terms of theta. These bounds are in terms of x. Now, it would be okay if you want to convert your bounds from x form to theta form, but we're kind of getting off the beaten path here. The whole reason why we're doing this problem is to practice the concept of anti-differentiating. If I'm really worried about the bounds, I'm going to the calculator anyway. It's a waste of time, right? At least in this class. So I'm going to ignore the bounds, do the work, and then bring the bounds in later on. So we're looking at the square root of 3 times the tangent of theta. All right. Oh, I didn't do my dx. Oh, I guess I could do it in a sec. I should do it now. Sorry. Dx is going to be equal to root 3 secant theta tan theta d theta. Right. Just that little extra step. It's not like, honestly, I've been doing this long enough. What did I say? It was 19th year teaching. More than half of that teaching this course. I'll tell you, nobody ever forgets the dx when they're doing a problem on this. They may not remember it in real time, but once you go to make your substitutions, you replace the radical with the rad 3 tan x, you replace the x with the rad 3 secant theta, and then you're like, oh crap, I got to replace the dx too. It always happens. So whether you do it now or you do it later, it gets done.
Shouldn't the A just be 3?
Shouldn't the a just be 3? I hope not, because then that means I have a lot of erasing to do. Like a lot. Like the kind where I have to rewind the video and start over.
No, I'm wrong.
Are you?
No, you're good.
Yeah,
Oh, I'm good. Oh, thank God.
I'm confused.
Yeah, but you see, even I hesitated. That's the kind of mistake you got to be careful about. So like, that's a me kind of mistake. Like I didn't even doubt it for a second that I screwed that up.
So are the ratios are going towards the constant always?
Always to the constant. Yep. All right. So on top, I have my radical 3 tangent of theta at long last. On the bottom, I have a radical 3 secant theta. And then my dx is going to get swapped out for this monster. Just double checking the monster here. Yeah, it looks good. Secant has a derivative, secant theta tan theta, so that's good. It's good. Yep. Okay. All right, so some things will cancel out. Yeah, not as much as we would have hoped, but yeah, there's some things. Let's get purple here. And we got rid of the denominator, so that can't be a bad thing. All right, so we're looking at the antiderivative of radical 3 times tangent squared theta d theta. All right. Now that's not something that we can integrate in this current form, but we can make a slight adjustment to it based on a substitution. Tangent squared theta is equivalent to an expression. And again, this is the theme that I keep coming back to. If you don't know enough to know when to look for a formula, then you've already lost the battle. So familiarize yourself with some of these rules. This is a Pythagorean identity. And it involves a secant squared. Does anybody know it? Secant squared minus 1, very good. All right, so we just went from something that we couldn't anti-differentiate into something that we very easily can. I've gone over this before. I like to distribute rather than pulling out the coefficient, only because, and I've explained this a bunch of times, but I'll keep explaining it. I always worry that I'm going to forget to rewrite the radical 3 later on, so I keep it as part of the action. It's like when you're at a party, you always stick with the group because you don't want to be left behind when they leave, and then you don't have a ride, so yeah, you don't want to be in that jam. So that's the radical, that's the coefficient. Coefficient, if it's outside the integral, there's no guarantee it's getting a ride home. You have to Uber it. Okay? But if it stays with the group, it's never going to get left behind. I'm going to move on, otherwise I dredge up traumatic events from the past. Like walking home from Queens to Manhattan. So, anyway, radical 3. Honestly, my brother couldn't wait. That's not cool. Antiderivative secant squared. Tangent. And the antiderivative of the constant is the constant times the variable. So minus radical 3 times theta plus c. So we almost have it. We just have to put the finishing touches on it. All right? So the tangent has to go away. I have a tailor-made relationship right there. So radical 3 times, and part of it's going to cancel out, which is even better. I just need some kind of expression to represent the theta. And I have choices. I have secant theta is equal to this. I have tangent theta is equal to that. Which means if I take the inverse secant of both sides here, I have theta. If I take the inverse tangent of both sides, I have theta for this one. Or if I want to create a brand new trig ratio from that triangle, maybe something that could possibly be simpler, doubtful, because the simplest one is always the variable to the constant. But you could still, I mean, if you want a sine ratio or a cosine ratio or whatever, you can do that. But I'm going to use the inverse secant of x over the square root of 3. So inverse secant of x over the square root of 3. All right. And so really the only bit of housekeeping that you can do here is to kill those rad 3's. That x over rad 3 is contained within the inverse function, so you can't cancel that second radical 3. So final answer, one of 6 potential correct final answers would be this.
After you find the integral, what do you do after that? Where you write in the radical 3 and the parentheses? What's that step?
From here to here?
No, from
From here to here?
One more.
Here to here.
Yeah.
This is actually taking the antiderivative.
No, the blue to the black.
Blue to the black. Oh, I'm just doing a substitution because earlier on in the process we knew that the tangent of theta was equal to the square root of x squared minus 3 over rad 3, so I replaced this with that. And then for the theta, any of the trig ratios, we could take the inverse of both sides, and that would give us that ratio. So all I did was just going back to this guy here. I took the inverse secant of both sides, and I got theta is equal to the inverse secant of x over the square root of 3. No problem.
So remember, I try to choose a theta for secant, another theta for tan.
You could. There's no wrong answer. You can go with whatever one you want. I just went with the one that I thought would be simpler, involve less writing. It's generally the name of the game there. All right, but that's definitely a beastly problem. Also, it's very easy to lose sight of the question, I guess. This one had bounds, right?
Yeah.
That's fun.
Would this be considered proof?
What's that?
Would this be considered proof?
Not really. Not really. I'll show you a proof related to this in a couple minutes, and you'll wish I didn't. No, it's not that bad. It's not.
So it's not just gonna be like trig identity. It's not gonna be like prove an identity. It can prove anything.
Yeah. I'll give you some examples in a little while. Basically, if we haven't done a proof in class, it's not something that I'm going to ask you to do on the test. All right? So, or at least some variation, because like on the last test, I didn't ask you to do the entire proof that we did in class. I just asked you to do part of it. So, all right, but anyway, I'm just going to ignore the bounds because again, if the bounds were, if we really cared about that, we would have just typed it in the calculator. All right, so if you really want to know what that answer is, ready to go. All right, so these other problems, I don't want to bore you to tears with this because it's just 3 more problems of the same idea. Well, at least 2 more problems of the same idea. The last one, I would say, is really the unique one. I do want to take an opportunity because it's, yeah, okay. So what I'm going to do is I'll take you through number 5, and then with that, I'll show you the little nifty shortcut rules related to this, because again, today's the nifty shortcut rule day, all right? So I'll show you the nifty shortcut rule related to that after we've kind of gone through this process, and then for that we'll use it for number 6. All right, so that's kind of where we're at, rather than actually just proving it to you and making you responsible for yet another proof. All right, so I think we're all in agreement there. So u would be equal to 2x, a would be equal to 1. If I want this to bear out as a radical 4x squared plus 1, I'm gonna have to place the 2x here and the 1 here, or vice versa, but this is the best way to place them. In which case I'd get a hypotenuse of 4x squared plus 1. All right. For this particular question, we're going to keep an eye on what u and a are. Okay.
So how are we getting 2x?
We're getting it by taking the square root of the term 4x squared.
Okay.
So it's always the square root of the two terms. It's just a question of which one's u and which one's a. The u is always the one with the x in it. The a is always the constant. A for constant. All right, so we get our ratios. One of them is the tangent ratio, tangent of theta, is equal to 2x over 1. But I'm just going to, well, I'll write it as 2x over 1. In which case we'd be looking at x equal to 1/2 tangent of theta. And since we know we're going to have to take the derivative of it again, or again as in like just like every other question, we might as well do it now. Dx would be equal to 1/2 secant squared theta d theta. All right, the other ratio is the secant ratio. Which is just the hypotenuse over 1, so I'm just going to write it as 4 root 4x squared plus 1. And I'm not going to write it over a 1 just to write it again without the 1, so I'm just going to leave it like that. All right. So we have all our ingredients here. I'm going to write my integral. Dx, 1/2 secant squared theta d theta, secant of theta. And there's no x to substitute in, so we're in good shape there, it looks like. Am I right? Am I right? Am I right? Yeah, there's no other x's. All right, so we're looking at 1/2 secant theta d theta, but it's still an integral. All right, so we have to integrate, which is obviously the fun part. All right, so let us get into that. Now, this is one of those moments. Four or five moments. You wake up a superhero. You brush your teeth a superhero. No, so yeah, this actually is one of those moments. You either know the antiderivative of secant, or you have to figure it out, right? But I had mentioned that regardless of whether it's tangent, secant, cosecant, whatever, you could figure those out using u substitution. But they're also your 6 trig functions, your 6 trig ratios, so they also fall under the category of facts. All right, so if you know the fact, you don't have to do the work. All right, if you don't know the fact, then you do have to do the work. All right, so Does anybody know the fact? The antiderivative of secant theta is?
ln secant x plus tan x plus c.
Exactamundo. So in this case, theta's. And the crowd goes wild. Yeah, it's just one of those things. Like, you have the rule, you're ready to rock and roll, or you don't have the rule, and rocking and rolling is not happening for you. All right, so great. Now it's just a matter of cleaning it up. So secant of theta is your root. We define that right here. Tangent theta. I mean, it's this one's nice because it's on a silver platter. I can't speak anymore. Tangent theta is equal to 2x, so plus 2x plus. I'll keep that blue. Plus c. All right. Now, all that being said, this was not the example I thought it was. So this is not us discovering a fabulous rule that we could then use as a shortcut. So that sucks. It's not the highlight of my day. But I'm still going to follow through and share with you the fabulous shortcut rules. I was going to put it on a timer, but I didn't know exactly when I'd get to this moment, so I'm just hitting send now. There you go. Yeah, look at that. So they're good rules. I'll bring it up on the big screen just so you don't have to rely on having your phones out and remind and all that good stuff. Let me just make sure it's up and not my personal emails and stuff. Let's see. It's got like student information and stuff. So. Like all your grades are up there. It's terrible. No, it's fine. Not at all. So these bad boys. It's pretty not bad. Right? So what we have here are, these are the shortcut rules for inverse trig functions. So they're kind of, I mean, I was going to say loosely related, but they're significantly related to the derivative rules that we created on our own, except they have some coefficients here that kind of work their way in. So what's happening here is that you're dealing with some nice relationships, but really only under certain circumstances. All right, so I'm gonna start jotting down stuff for the next example and show you how it comes into play. All right, I know it's not on the screen, but the next one is very much like the arc secant rule. Although actually I don't even know if it applies in that case. I'm going to change the example so that it actually works, because I want to actually make this work out nicely for us. Yeah, it definitely wouldn't work. All right. So I'll jot the rule down and I'll show you what I'm talking about.
Do you have, since there's so many rules for this unit, do you have specific ones that you recommend that we put on index cards?
Inverse trig rules. Integration by parts. Trig identities. Should be it, because everything else is a concept. Yeah, like use substitution if you gotta.
The really big antidifferentiator ones.
Those are the big ones, because everything else are really concepts more than anything else. Yeah, if you know those, I think that's the way to go. Like that's the main focus. So I'm going to take you through an example related to the arc secant rule. All right, so I'm just getting it down on here so I don't have to flip back and forth. All right, so HTML1. There we go. All right, so I changed the problem so it actually fits what I'm trying to teach right now, ideally. So this is the kind of question where, and I'll take this as a typo. So if that's something you're interested in. I got like a good 4 or 5 people that are maxed out on typos already, which is good news for you. So, if you've been late to the party on these things, you've been submitting them and not getting them, you'll find that moving forward, when you submit them, you're going to start getting the bonus points because a lot more people are getting out of the way now. All right. So we can apply this rule just by knowing this information. Now, I'm not going to bore you with taking you through the entire trig substitution approach. But if you're looking at something that follows the same structure as one of the inverse trig rules, but differs only by 2 things, 2 possibilities. One would be a constant, all right? So instead of the 1, you have a 9 in this case. Or, this is the weird part, or a variable whose derivative is nothing other than a constant. All right, so that's kind of a weird thing. So, like, you can have, let's say, instead of x squared, you could have 4x squared. All right, you could have pi x squared, but you can't have something like sine x squared. All right, without having some other term on the outside of that radical that is the derivative of that u. All right, in which case it would just become ordinary u substitution. All right, so that part is the weird part, but basically, general rule of thumb, look at your integral, look at one of these shortcut rules that you're going to put down on your index card. If it looks like it's almost a perfect fit except for a constant or maybe just some slight modification to your variable, then try using this technique. All right, the good news is, this technique only relies on your ability to identify u and a. All right, so u is x, a is 3. And so my answer would be, wait for it, 1/3 inverse secant absolute value of x over 3 plus c.
Is that a valid move on the test?
That sure is. Which is what I was talking about before, where I was saying I'm not going to necessarily tell you specifically how to do it because I want these little bits of insight, these aha moments during the test. Like the shortcut through the maze to come into play. The savvy student to be rewarded, So I always like to have it in mind that people should be, like students, when you're taking a test, you should be rewarded if you give a question a little bit of extra thought. All right? If you take some time and think about it, consider the question, the payoff should be that, aha, I got it. Now I don't have to do as much work. Whereas if a person just dives in and just starts doing the work, you'll get the right answer. There's no penalty. But you can take a little bit more time to do it. All right? Now, I think I already know the answer to this. I could go through this using the trig substitution approach, creating the triangle, doing all that work, and prove to you that this is the result. But like I said, I think you're fine with me just moving on. No, we're not, I guess. What's that?
For question 5, we could use one of the rules.
Unfortunately, for question 5, you couldn't because I had started that question being like, we're going to discover a rule, and then I was thinking of the wrong question. So that was on me. That's like the Rogue One trailers. Half of the images weren't actually in the movie.
You can leave it as arc secant too, right?
Yeah, you can write it as arcsecant also. Yep. And in this case, and just to address something that may not have even crossed your mind, but eventually it might. In these other questions, we had secants and tangents that we had to get rid of. You might have it in your mind, oh, if there's trig in here, I have to get rid of the trig, just like we did there. Because understand, it wasn't the trig that we had to get rid of. It was the thetas that we had to get rid of. All right, thetas had to go away. Once the thetas were gone, we were good. All right, so if I had tangent, secant, inverse secant, whatever, in my final answer, that's fine, as long as I don't have the thetas. Thetas are the problem, all right? So just something to keep in mind. All right, so let's take a look at the pièce de résistance. You're like, this doesn't look like any of these questions. How on earth are we going to do this? All right, well, I will tell you that there is a technique that one could use to take a trinomial and write it as a binomial. All right. It's one of those techniques that you definitely know. It's just a question of whether you would ever think to do this. All right. So what I'm going to do is I'm going to take that 8 and I'm going to write it as the sum of two values. All right. So the idea is that I want this part here to be a perfect square trinomial. All right, so in order to do that, I need to complete the square. So right back to algebra 1. So different techniques, different teachers use different approaches. I like the formula approach, at least on this level. When I'm teaching it for the first time, I teach it differently. But, years later, it's like, all right, you need the quick and easy way to complete the square. B squared over 4a. Which is the same as taking the b value, cutting it in half, squaring it, and dividing by the leading coefficient. All right, so my b value squared over 4a. So the one weird thing is this trinomial, this quadratic trinomial, is written out of order. So the first one would be the c value, then the b, then the a. So you just got to keep that in mind. But it's basically telling me that I'm going to put a -2 right here, and I'm going to put, there's an understood -1 here, that's going to go right here. And so the result of this is going to be a -1. That's the value that will complete that perfect square trinomial. That's going to go right here. All right. Now, these two numbers have to add to equal 8. Right? Otherwise, it's not an equivalent relation. So what does this number have to be? 9. All right. All right, so I have a 9. Now what I'm going to do is I'm going to factor out a -1 here. All right, because there's a common -1. I can pull it out of the whole thing. That's going to give me 1 plus 2x plus x squared, which is a perfect square trinomial. What are its factors? Should be a binomial squared. Give me two numbers that multiply to 1. 1 and 1. Give me two numbers that multiply to x squared. x, and x. So 1 plus x. All right, so we just completed the square to write a trinomial as a binomial, where this is one term of the binomial and this is the other term of the binomial. All right, so my new integral is going to be dx over the square root of 9 minus 1 plus x squared. All right. Now, you look at this and say, okay, well, that's cool, but what on earth did that accomplish? This is in the same form as an arc sine derivative. All right, so if I'm using my arc sine antiderivative rule, I'll show you real quick again. Hopefully, yeah, it's still on. A squared minus u squared. Constant squared minus variable squared. It's just the variable's a little bit beefier. It's 1 plus x rather than just an x. But still, that's fine. By the way, what is the derivative of 1 plus x? Just a 1, all right? So the derivative of the u part is constant, so these rules would apply. All right, so as long as your u part has a derivative that's constant, you can work with this technique. So once I identify my u and my a, I'm done, all right? So the hard part is actually over. So the u is going to be 1 plus x, and the a is going to be equal to 3 because it's the square root of each part. And so my antiderivative is going to be the inverse sine of 1 plus x over 3 plus c. All right, now, well, two things. Obviously, this is completely reliant on your ability to recognize that this trinomial is something that you could work with using an inverse trig approach. All right, so that's the first thing. And then the second thing that I would say, obviously, too, is the fact that it's in the trig substitution section and there's a triangle there, which means that you could do this problem also with the triangle approach. However, if you can't recognize that this is something that you could write as a binomial, then it's all over, you know? And so you have to kind of keep it in your mind that any, and that's any, like any trinomial can be written in binomial form. That's the standard form of a quadratic. All right, so just so I can make sure I can sleep at night, I suppose, I'm just going to quickly show you one more example involving just the completing the square part. So let's say you have 2x squared minus 4x plus 7. And I want to write that in binomial form. All right. So that means that I'm looking at 2x squared minus 4x, and then I'm going to have the sum of two values that need to result in a 7. All right. Now, bear in mind, I mean, you might look at it and say, well, I'll just do guess and check. Maybe it's a 1 and a 6. All right. Yeah, that's all well and good, but it could also be like 24/7 plus 24. Forget it. I was going to say 24/7, but that would actually end up giving me a 4 once I added what I was going to add. So, but it could be fractional, it could be radical, it could be, you get the idea. All right. So b squared over 4a. So negative 4 squared over 4 times 2. 16 over 8 is 2. All right, so I'm going to put a 2 here. All right, but the two values need to add to give me a 7. So the other number has to be what? 5. All right, so I take this trinomial, factor out a GCF, because I have a common 2. And then factor the remaining trinomial. All right, so you can see 2 terms. 1, 2. Binomial form. All right, it's also the standard form of a quadratic, but that's not really important. Now you can manipulate this if you want. If I was looking at an equation, I could divide everything by 2 to give this no coefficient. If I wanted to, I could even leave the 2 inside and work with radicals. I don't know why I'd want to do that, but you know.
The way to solve it is 2 numbers that multiply to whatever the squared value is, and then add to whatever the single x is.
You're talking about,
Like the way you solve the quadratic equation, you said it's 2 numbers
from here to here?
Yeah.
Yeah, so 2 numbers that multiply to this, and then 2 numbers that multiply to that. It's only for perfect square trinomials. Yeah, you're just taking the square root of the first and last terms and carrying down the middle sign. No problem. Okay, so, you know, it can be helpful.